look at the concept of hybrid or piecewise graphs. This is just a very, very fancy and over-the-top way of describing how or giving the set of instructions where I put 3, 4, 5, however many graphs I want, all on the same axes. So instead of saying, draw this one and this one, this one on the same set of axes, we now have a very convenient way to be able to express that in a very efficient and mathematical way. So, as I do like to start, as per usual, with an opening problem. Consider the following graphs. You see, they have been written in what is known as function notation. So what that means is that we've got the little names for the graph. So remember that these are the names. And then it has these numbers here. So this has got -3, 4. We've got a 4, 5 here and a 5 to a positive infinity. Of course, that means the domains. So that means where do the x's start and where do they end on a graph from left to right. Now, you remember it says the arrow and the R value there. So what that means is that the range is a subset of all real numbers. So you should always see an arrow and an R. So the range is a subset of all real numbers. No surprise, fake numbers here or imaginary numbers for us to deal with. You keep that with your specialist and your complex numbers. And then we've got f of x, g of x, h of x. The x indicates what our variable of choice is. In this case, it's an x. And then we've got the equations of our lines. So, the first question says we need the domains for each one. Well, thankfully, they've all been delivered rather nicely on a platter for us. So for each of these, I just have to copy down what the sets of instructions have to say. So we've got -3, 4, 4, 5, and -5, well, just -5, and the positive infinity. And as a reminder, well, we've got the little square brackets. Remember, that means including. And then we've got the, let's get a different color. What color shall I use? I'll use a big old red color. We've got the round bracket. That, of course, means not including. The next question asks us to find the ranges. So the ranges means the list of y values. Now, in order to find the y values, we'll need to substitute the x values in. So what we're going to do is we're going to take the domains, find the two ends of the domain, and then substitute those into the equations, the respective equations, and that will tell us what the maximum and minimum y values are. It also would help us to know, just as a general principle, what the shape of each graph is. The first two, f and g, are both linear. So I know that the first one, for instance, -x plus 4, is going to look something like that. And then g, it's a positive linear graph, and it's going to look something like this. And h is a quadratic, and it's moved over to the right by 5. So it's going to look something like this. This will be very useful so I know where my ranges and things or the shape should look like. So I'm going to start with f. So I'm going to start from -3 to 4. So I'm going to start by getting my lovely values sorted out. So what I'm going to do is sub x equals -3. So this is -3 plus 4, which gets me to 3 plus 4, which is 7. And at the other end, which is 4, I'm going to sub x equals 4. That's going to be -4 plus 4, and it's going to be 0. So that means the lowest value, or the lowest y value, is going to be 0. Highest value is going to be 7. We know that when we substitute -3, it's not including. So I'm going to have to put a not including here of 7. And why did I put 7 over there? Because when we write our ranges and our domains, we put the smallest number on the left, largest number on the right. And the 4, when I substituted that 4 is including, so I'm going to put that 4 there. Oh, no, silly, Mr. Innes. We have to put the 0 in there. That is, because that's the 0 from here. Boop. That 0 there goes there. And because that 4 was including and had an including bracket, that 0 has to have the including bracket in there. And then we've got the 7, which is going to go over there. So now what do we need to do? We need to go and get the ones for the G. So the G I'm going to substitute in there. I'm just going to put my green for G here. I'm going to sub x equals 4. And that's going to be 2 times 4, take away 3. 2 times 4 is equal to 8. Take away 3 is equal to 5. It's very nerve-wracking having to do this arithmetic in front of an audience. So then we're going to do, what's the other one? 5. So we're going to substitute x equals 5. So 2 times 5, take away 3. 2 times 5 is 10. And then 10 take away 3 is equal to 7. So again, we're going to write from left to right. Now, let's have a look. That 4 is not including. So that means this 5, the one that's attached to this 4, is not including. And the 5 up here in the domain was not including. So therefore, the 7 is also not including. The H's. Let's get our H's on. So I'm going to substitute x equals 5. Now, hopefully, for those who are already quite aware, we know that this is a quadratic, is moved over by 5, we reckon we can probably figure out what the value of this is going to be. The formula here is x minus 5 all squared. So we're going to go and do 5 take away 5 all squared. And of course, it's equal to 0. And I can't substitute infinity, so thankfully I know the shape. It's just going to keep going on forever. So I know the 5 is including, so the range is 0. And it's going to go to infinity because the graph is pointing up this way. It's going up. So now I have to sketch this, friend, all onto this graph here. So what I'm going to do is I'm going to put some very approximate scales here. I know normally I'm all very much about not putting numbers in. So for the first one, we're starting from the domain of -3, and at -3 it is 7. So for the first one, the value for f, it's going to start here, and it's not including. It's going to be a great big open circle over here, and it finishes at 4. And at 4, it has a value of 0, and that is definitely including. So we're going to put a big old dot here. And what I'm going to do is I'm going to get my little straight line tool here. Come on, dear. There it is. And we're going to go and draw a line like so. There we go. And it should have a y-intercept of 4, and thankfully my drawing is somewhat accurate. The next graph of G, so what I might do is be a very good maths method student to make sure I label my endpoints. So this is -3, 7, and this is 4, 0. And this is the graph of f of x. And then for G, we start at 4, but it's not including, and it's 4, and it's the coordinates 4, 5. So we've got 1 there. And then at the coordinate 5, which is also not including, we've got 7. So it's going to be like that. And what I'm going to do is going to get my green line going. There we go. Oh. Get that in there. Remember that the open circles mean not including. The coloured in circles means it is including. And then finally, with the orange, the ones here, we start at 5. So it's 5, 0. And we can't draw a straight line. It has to be a curve. And it is the turning point. So it should look something like that. If you really want to be super accurate, and we're always happy to be super accurate, if I substituted x equals 8, 8 take away 5 would be 3, so that should actually be at 9. So actually, I'm not going to be happy until I draw a nicer one. There we go, that'll do. That's close enough. And that is h of x, and this is, and I can write that coordinate here as 5, 0. This is g of x, and this end is 4, 5, and this is 5, 7. And we have drawn them all on the same axes. So, with a hybrid function is one of two things. One, it's still a function. And two, it's just a set of instructions to build a series of functions that we smush together on the same axes. So what makes it a graph of function? Remember, it has to have a vertical line going straight through. So you might see in each of these points, this is an example of a hybrid function. You'll notice sometimes called piecewise function. I'll have none of that. I was brought up back in my days. It was called a hybrid function. It's going to stay a hybrid function. So you'll see here that at this point, at x equals 4, we've got a dot at the bottom and a dot at the top. But because the dot at the top is not including, I can still draw a straight line, and technically it only goes to the graph once. So this is still, by all means, a function. Similarly, when x equals 5 as well. Now let's call this, so what we're going to do is I'm going to show you how this is written. So at the top of this sheet, you'll see here, we write them in this sort of format here. You'll notice here that when we draw them, we put any letter. I've just put H for hybrid, but it doesn't matter what we call it. Since we already have an H of X, I might give it a different name. I might call it J of X or something like that. So what I'm going to do is I'm now going to turn this question into writing it as a hybrid. And now it's time to actually write this as a hybrid function. So because I've already got f, g, and h, I'm just going to pick another letter. I'm just going to call this j of x. I could call it whatever I like. And then what we do is we put a brace, otherwise known as a curly bracket, or as some of my previous students have known to call it a mustache bracket. And what we do in this is that we actually go and put each of the equations down. So negative x minus 4, 2x minus 3, and x minus 5 all squared. And then what we write is we simply write what the domains for each are. So x is an element of negative 3, 4. X is an element of 4, 5. And x is an element of 5, infinity. In order for it to be a function, we have to make sure that the endpoints of each of the domains that we put on there, one has to be including, one has to be not including. If they are both including, then it's no longer a function. It would be a hybrid relation, I guess, would be the best term for it. Here I've got a hybrid function, and I'm asking you to find the equation for it. So in other words, we're going to find the equation for each component, and then we're going to write it as a hybrid function. So we can start with this one on the left. It's clearly including. At this point, it doesn't actually suggest it's including or not including, so we can make that decision ourselves, but we'll start with this. The best way, if it's a straight line, is that we need to find the equation of a straight line. This is at negative 3, 3. It's at negative 6, negative 6. So we can find the gradient by going 3, take away negative 6, negative 3 minus negative 6. So this is equal to 9 divided by 3, which is, funny enough, equal to 3. This becomes y equals 3x plus c. And then we can substitute one of these points. Let's just do 3 is equal to 3 times negative 3 plus c. 3 is equal to negative 9 plus c. And then that's going to be equal to 12 is equal to c. So that's going to be equal to y is equal to 3x plus 12. If you're ever the kind of person to worry if your calculation doesn't make any sense or anything like that, one of the things that I would suggest is get to the graph and just make that line a little bit longer. And ideally, you want to see whether or not it hits the axis. Here, it's clearly hitting above 10, so I reckon we're pretty much on the money. So one way to look, the reason why I say this is when in one of my early drafts of doing this particular exercise, I kept getting this wrong. I ended up getting something along the lines of a y-intercept of 4, which didn't make any sense. Turns out I said 9 divided by 3 was 2. So having the visual can be very helpful. All right, let's get pink going on here for this middle component. And from here to here. And we'll label this as 5, -1. So again, for the middle component, I'm going to go -1 minus 3, 5 minus 3. So this is going to be -4 over 8. So this is -1/2. Y is equal to -1/2 x plus c. We can substitute in here, so we can either use 3 and -3 again. Why not? You did very well the last time. Times -3 plus c. So 3 is equal to 3 over 2 plus c. So 3 over 2 is 1.5. 3 take away 1.5 is 1.5. So that's going to be 3 over 2 is equal to c. So therefore that's y is equal to -1/2 x plus 3 over 2, which makes sense as the line is going right through 1.5. For the last component, I'll get my orange line. From here to here, we can see the end is not including, so that is helpful knowledge for us to know. Gradient, that is 7, 3. So 3 take away -1 over 7 take away 5. So that's 4 take away 2, which is equal to 2. That one's definitely equal to 2. Y is equal to 2x plus c. And this is going to be 7. No, silly me. Wise. 3 is equal to 2 times 7 plus c. 3 is equal to 14 plus c. C would equal to -11. And so this is going to be, just want to make sure I've done that right. 2x, if I had done that correctly. 3 and 7, yep. 14, -11, yep. And now we have our 3 equations. So now all we need to do is write the hybrid function. So the hybrid function, which we can call h of x, has these 3 components. So 3x plus 12, -1 over 2x plus 3 over 2, and 2x minus 11. And then all we need to write is the domains for each of these. Now we've got some flexibility as to what domains we choose. So we definitely know that that -6, the x value, is including, because it's a colored in dot. Now for the next one, we can actually choose if we want to have that as including or not including. It doesn't matter. Just for the sake of clarity, why not? Let's make that including. So the next one, the pink section, is going from -3 to 5. We can't have 2 includings, only 1 has to be included, so we'll do -3, and again I'll put 5 as including, like so, and then the last one goes from 5 to 7, because that's the domain there, from 5 to 7, the x values, so we'll not include 5, and according to that it's a very open dot, so it will not include 7. Please remember this and this brackets here are interchangeable. both are correct. So if you made that's 5 not including and the 5 including, that is fine. And similarly, this bracket and this bracket are interchangeable as well because they are connected here. So that interchangeableness is only applicable to graphs that are connected. This is a connected graph. It's not a continuous curve, well, it's kind of a continuous curve, but not really. But the fact that they are joined up means they can be interchangeable. However, these cannot be interchangeable because you'll notice here that the 3 components are not joined together, so they have to be written the way that they are. So that they must be written in that way. Here we have some flexibility.